Question 2 from Section 2 of the 2022 Higher Physics Examination from the SQA. A student carries out an experiment to investigate friction between a puck and the surface of a table. The student measures the mass m of the puck, and the student pushes the puck and releases it at point R. The student measures the initial speed u of the puck as it is released at R. And the puck travels a distance d before coming to rest in the centre of the target. The student records the following measurements. The mass of the puck was 0.350 kilograms. The initial speed of the puck was 0.78 meters per second. And the distance travelled by the puck d equals 2.160 meters. And for 3 marks, we're asked to calculate the average acceleration of the puck between point R and the centre of the target. Well, we start off with our kinematics, which is a kinematics problem, with our kinematic variables, u being the initial velocity, v being the final velocity, a being acceleration, s being the displacement, and t being the time. The initial velocity of the puck is going to be 0.78, so we're told that. And that's the first bit of data put in. The final velocity is going to be 0 because it's come to a rest in the centre of the target. The acceleration is what we're after, and the displacement, we're told, is going to be 2.160 meters. And we don't need anything about the time. So we have got u, we've got v, we've got a, and we've got s. So we look up our relationship sheet and find a relationship which has got all those 4 characters in it, and we find out we end up with v squared is going to equal to u squared plus 2as, the equation, kinematic equation with no time involved. We have to rearrange to find a, so remember we've got to find a out of this. So our first port of call is to take u squared over the other side, and we should be well rehearsed doing this. V squared minus u squared is going to equal to 2as. We want to find a on its own, so we have to divide both sides by 2s to get what a is. So v squared minus u squared, I'll put a bracket around that, divided by 2s, and that's going to give us the value for the acceleration. So now we've got the acceleration, we can plug in the numbers. Acceleration is going to equal to the final velocity squared, 0 squared, take away 0.78 all squared. And we're going to divide that by 2 times the distance, 2 times, and the distance is going to be 2.160. Put that in a bracket, do that in my calculator, and we end up with a value of minus 0.14, and that's going to be 141, and that's going to be meters per second every second. And you can see that the acceleration is negative because the puck is slowing down, so that's going to be the average acceleration minus 0.141 meters per second per second. Question 2a, continued part 2. Calculate the magnitude of the average force of friction between the puck and the table. It's the force which is causing the force of friction which is causing the puck to decelerate, and therefore we can use the formula F equals ma, Newton's second law. F equals ma for that one. We know the acceleration because we just worked it out, and the acceleration was minus 0.141 meters per second every second, but we can drop the minus sign as we're only interested in magnitudes, not directions, so we just use the positive value of that. And we also know the mass of the puck, which was measured, and that came out to be equal to 0.350 kilograms. So the force is going to be equal to ma, so into our equation go the numbers. Force equals 0.350 and multiply by acceleration, just take the magnitude of it, 0.141, and we work that out in our calculators, we get a value of 0.049 newtons. And that's the force of friction which is acting between the puck and the table, causing the puck to decelerate. Question 2b. The student determines the absolute and percentage scale reading uncertainties for each of the measurements, and he's displayed them there in a table. The student makes the following statement on that table. The best way to reduce the uncertainty in the value calculated for the average force is to use a balance that measures to the nearest 0.0001 kilograms to measure the mass of the puck. And we've got to explain for just 1 mark why that student's correct statement is incorrect. Well, if you look down the percentage uncertainty, you can see that it's going to be the initial speed of the puck, which we're going to use as the overall percentage uncertainty in our value calculated for the average force. That's the one we're going to use here because that's got the biggest uncertainty. If the student goes ahead and works with a balance that measures to near 0.001 kilogram, then the absolute uncertainty is going to in fact decrease by another tenth, but the percentage uncertainty will decrease as well, but that's not going to affect the overall percentage uncertainty which we're going to use for the experiment. We always use the biggest one, which is this one here. This is by far the biggest one. So the very fact that the student is going to concentrate on reducing the percentage uncertainty of the mass of the puck will make no difference in the overall uncertainty of the value, because we're still going to have to take the largest value, which is the initial speed of the puck, and the percentage uncertainty for that is 1.3%. So because that's unaffected and that's the biggest, well, the student's statement is incorrect.